Hello, this is Math 2270 coming to you from the College of DuPage during the summer of 2020, and this is the second continuation of the lecture entitled A Gentle Introduction to Infinite Series Solutions for Differential. So consider a differential equation that looks like this. But this time we really are going to allow the non-constant coefficients. Series solutions are the most general way that we can have non-constant coefficients differential equations. And to make the problems a little nicer computationally, in the examples that I am doing now, we're only going to deal with polynomial coefficients. So P of x and Q of x and R of x are going to be polynomials. Now we say that x equal x0 is an ordinary point if provided both Q of x over P of x and R of x over P of x are analytic at x equal x0. Remember, that means that they have Taylor series about x equal x0. And since we're only dealing with coefficients that are polynomials, this is equivalent for them to say that P of x0 does not equal to 0. And again, you see what we're doing is we're dividing through by this initial coefficient like we've done time after time in this course. If a point is not an ordinary point, we call it a singular point, and different infinite series techniques must be used. But here, the basic idea is to find a series solution to a differential equation, and we're going to assume that we can write the solution as a power series. That's why we studied those in this form about x0. And we have to determine what the ANs have to be. We will only be able to do this simply if x equal x0 is an ordinary point. More complex things are required for singular points. And so that's what we're going to do. Let's go through an example. So we're going to determine a series solution for the following differential equation about the point x0 equal 0. So this is y double prime plus y is equal to 0. Now notice that in this case, the term I called P of x, which was the coefficient here, is 1. So every point is an ordinary point. But we're going to be looking for a solution in the form of y of x equal the summation n equals 0 to infinity an, and this is x minus 0 all to the n, and that just makes the notations easier. So we're going to be talking about x0 equal to 0. Well, let's take some derivatives. So we take the derivatives term by term. So y prime is going to be this. Now notice that I dropped off the a0 term because I took a derivative of a constant, and that was 0, and so this sum goes from n equal 1. But since I have n listed here, I could change that to n equals 0 if I wanted to, and I probably will later. And then this is going to be, the derivative of each term is going to be n, an, and then that is x to the n minus 1. Let's take the derivative again. Now this time, what I had was a1 was a constant, and so this one could start at n equal 2. Taking the derivative again of this, I will have n times n minus 1 an x to the n minus 2. But notice that since I have n here and I have n minus 1 here, I could change this to being n equals 0, and it would still be the same thing. So now what I'm going to do is I'm going to add these two things together down here, and I have this. Here is the y double prime, and here is the y prime, and we're setting it equal to 0. Now we want to combine this into a single series, and to do this requires that we get both series starting at the same point and having the exponents be the same. This is what we did with the indices before. Okay, let's start this by getting the exponent on the x to be the same. And it's usually best to try to get this exponent to be n. Now the second series already has the proper exponents, and we need to do some shifting. So what we do is we shift this down by 2 and increase these by 2. And this one already had the correct indices. So now I have what I really basically need, because we're starting at the same place, n equals 0, and we're having the same exponents. So now I will combine these into a single series and factor out the x to the n. But now we have the property saying that, oh, the only way that a power series is equal to 0 for all x is if this is equal to 0, the coefficient. So this is equal to 0 for n equals 0, 1, 2, and so on and so forth. Now what I'm going to do is solve this. This is called a recurrence relation, and I'm going to solve it for the highest power of, or highest subscript rather, of in the recursion, and that's going to be n plus 2. So I'm going to solve this for n plus 2. And I get this, an plus 2 is equal to the negative of this over this, for n equals 0, 1, 2, and so on and so forth. Now, this is where you're going to be spending quite a bit of time after you do this, but now at this point, we just start plugging in some values and see what happens. So for n equals 0, I get this. For n equal 1, I get this. For n equal 2, I get this, but I know that a2 is this, so I substitute again and I can simplify it this way. So you see, I've got both this term and this term have a0. We go over here, when n is 3, I have this, but I knew that a3 was this, so I can substitute and I get this expression. So you see, what happens is, for each of these, by doing repeated substitutions, I can have all of these coefficients be in terms of, here's what I get for n4, here's what I get for n5. So you see, I'm trying to see, can I discern a pattern? And I do discern a pattern. And this is the pattern. The even coefficients are going to be minus 1 to the k over 2k whole factorial times a0. K equal 1, 2, so on and so forth. And the odd terms are going to be minus 1 to the k, a1 over 2k plus 1 whole factorial. So that means when I go back, I know what these look like, and I can substitute all of those values in. Dot dot dots here mean I do things in between, and dot 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 means I just go off to infinity. But now you see, I can collect terms. I can factor the a0 out of a bunch of the terms, and I have this left. I can factor the a1 out of the other terms, I have this left. And when I write this in summation notation, I can write it this way and this way. And we're really done, except we really would have known how to solve that equation to start with, and it would have been c1 cosine x plus c2 sine x, and that's exactly what we got. The c1 and c2 are replaced by a0 and a1. Now here's a problem. Find a series solution about x0 equals 0 for the following differential equation. But notice this time I'm having a variable coefficient. But you ought to be able to handle this now. You know what to do. And when we return in 23.3, we'll see how you